Let's get started. Hello, everyone, and welcome to the first keynote talk of the third day at FSTTCS. It's my pleasure to introduce Professor Uriel Feige. Professor Feige is a faculty in the Mathematics and Computer Science Department at the Weizmann Institute of Science. He completed his PhD in 1990 with Adi Shamir. Professor Feige is a household name for people working in algorithms and complexity, and his results on hardness of approximation find frequent mention in papers and conferences, including at FST. Professor Feige was awarded the Gödel Prize in 2001 for his work on the PCP theorem and has received the Fox Test of Time Award in 2021, as well as numerous Best Paper awards. His talk today is in fair allocations with little communication, so let me take the hint and allow him to communicate. Please welcome Professor Feige.
So thank you. So I want first to thank the organizers for organizing such a wonderful conference and for inviting me to be part of it. And I'm really enjoying it. The title of the talk is Fair Allocation with Little Communication. So I'll start just with the basics. We will consider allocation of indivisible items. So in our setting, there will be n agents and m items. Each item is indivisible. And in this talk, we'll think of items as goods, items that the agents want to receive. And allocation of the items is a partition of the set of items into n disjoint bundles, and you give each bundle to an agent. So, for example, here the four items would be the sun, the moon, the star, and a cloud. And a partition, maybe the red agents get the sun and the moon, and the green agents a star and a cloud. So again, the setting is that we have m items, which are goods, and n agents, and we want the allocation to be fair in some sense, okay? So in order to define fairness, we have first to say, like, what does each person deserve to receive? So we think of the agents as having equal entitlements, so nothing distinguishes between them, all should get the same treatment. And one way of achieving fairness, let's say, is that people pay for what they get. This is some sort of fairness. Here, there are no payments, and agents don't transfer money between them. So examples can be, one example would be allocating housing units to eligible residents. So what you see here, let's see if it shows here, this like in Israel, we have this government program of giving housing at discount prices to eligible young couples, let's say. And so this would be an example. They do pay for the houses, but the right to participate, they have like equal rights. Assigning course slots to students, inheritance of, let's say, jewelry to several daughters. So you might think of the jewelry as being, each piece of it as being indivisible. And there are multiple other examples. So to define a fair allocation, we need to assume something about what agents want. And so our assumption would be that each agent, and this is a standard assumption, each agent I has a personal valuation function over subsets of items. So for each subset of an item, it has a value. And here, for concreteness, we assume that the value is a rational number and not arbitrary real numbers. We assume that valuation functions are monotone, meaning that if you get nothing, the value is nothing. And, normalized, and that they are monotone. The more you get, the more value you get. The more items you get, the more value you get. And in our setting, a fairness notion classifies the allocation as fair or not fair towards the agent, based only on the agent's valuation function. So this is an assumption that these are the kind of fairness notions that we will be dealing with here. Only those that are of this sort, that you judge if an allocation is fair only based on the valuation function of the agents. And if all agents find it fair, then the allocation is acceptable. So this is a special case of what's known as ex post fairness. with anonymous agents. There are other notions of fairness like procedural fairness, that the allocation procedure is fair, or ex ante fairness, where you have distributions over allocations and the distribution has to be fair. There are other notions, but this is what we'll consider here. And we'll discuss the communication complexity of allocation algorithms that allocate the items. So initially, only the agents know their own valuation functions, and they need to somehow communicate it to the algorithm so that the algorithm can produce a fair allocation. And the question is, how much about the valuation functions they need to reveal? Do they need to describe it completely, or is it enough to describe only some parts of it so that you can get to a fair allocation? We only measure the communication from the agents to the algorithm. Let's say if the algorithm asks queries to the agents, so the query itself does not count as part of the communication. Another way of thinking of it, so one reason for this is we just care how much information about the valuation function is revealed. So questions that you are asked are not part of the information. And another way of thinking of it is that the agent just broadcasts this information, and each agent can run the publicly known algorithm privately. So there's really no communication to the agents in this case. And we will allow randomized protocols or algorithms with public randomness. And in this case, we'll measure the expected communication. And another thing that we're going to do is look at it on a per agent basis, not like the total communication, like it's the same, but on average per agent. It would just, the results appear nicer this way. Okay, so what will we do in this talk? So first, one thing agents can always do is just send their full valuation function, and then the algorithm computes an allocation. We don't count the complexity of computation, just of communication. So how much does it take to communicate a valuation function? We'll discuss this. Then we'll discuss some classes of fairness notions and set our expectations based on these classes, which classes we expect to require more communication, which classes of fairness notions might require less communication. Then we'll present a bird's eye view of the results and like explain where the interesting stuff is going on in these results. And another thing we'll discuss is, this comes up a lot in like game theory, algorithmic game theory. Like, do agents have incentives to tell the truth? We have an allocation algorithm. Why should they tell the algorithm the real valuation functions? Maybe by manipulating what they send, they can reach better results. So we'll discuss this. And then we'll get to some more details on the results and the proofs. And this part is flexible depending on the time that we have. We'll see more or less or fewer results. And at the end, we'll mention some open questions. Okay, any questions up to here? Okay. Okay, so how much does it take to communicate a valuation function? So we said each agent has a private valuation function, and we assume that the values of each possible bundle is a rational number. So there are, if there are m items, there are 2 to the m possible bundles that you can create, and each one has a value with a numerator and denominator. So if we assume that R is an upper bound on the numbers that appear in the numerators and denominators, then you can communicate the full valuation function in time. The communication is order of 2 to the m, because that's the number of bundles, and log R, because that's the precision you need in order to specify the numbers involved. If you don't want a dependency on the numbers involved, and we often don't want it, then something that works in our favor is that many fairness notions are what we say, what we call ordinal. All they depend on is the order among the bundles, which bundle is better than which other bundle of items, and not the exact value. So if you just want to transmit the order among the bundles, there are 2 to the m bundles. So you can do that in 2 to the m times m bits. So now the complexity depends only on the number of items and not on the actual values. So this is for general valuation functions. But we will consider also a special class of valuation functions that we call them item-valued valuations. In this class of valuations, each item has an individual value. And when you want to see the value for a set of items, there's a simple aggregation rule that tells you what's the value for the set. So well-known classes of this form are the unit demand class. So the value of a set of items is the value of the best item in this set. Okay. Another case would be additive. The value of the set of items is the sum of values in the set. Another example would be what's known as budget additive, which is the value of the sum of values of the items, but if it exceeds some budget B, then the value becomes just B. So for these valuations, they can be communicated using m times log r bits because you just need to specify the value of each item. And if you want just the ordinal valuation, there are not so many possible orders that you can create using, let's say, additive valuations among bundles. And if I'm not mistaken, so this is something I prepared for the talk, but you can always transmit it using order m squared bits. So you don't read exponential in m in order to get the ordinal value, like the preference order over bundles. There are not that many possibilities. Okay, so now let's go to fairness notions. So there will be two main classes of fairness notions. One is share-based. So in share-based fairness notion, each agent computes what they believe to be their own fair share. So based on their own valuation function, they say, how much value do I deserve to receive? And the most common share that is used is the max-min share, which is basically what would happen in a sort of cut and choose protocol. So if there are n agents and I'm one of them, I get to partition the items into n bundles in any way that I want. And then I let the other agents choose first which bundles they get, and I get the last bundle. So the value that I can guarantee myself in such a protocol is the max-min share. So I will try to partition the items into bundles that are such that the minimum bundle in this partition is as high as possible value. And that's my max-min share. So this is one class of fairness notion, share-based fairness notion. I care about what I get. I don't care about what other agents get. Another class is comparison-based fairness notions, where I compare myself to others and I want to get something, let's say, at least as good as the others do. So the most well-known fairness notion here is envy-freeness, where I want a partition in which for each agent, from her point of view, the bundle that she received is at least as good as the bundle as that any other agent received. Her value for her own bundle is at least as high as that for any other bundle. An important thing that will come up in this talk is feasibility of fairness notions. So some fairness notions, we say that the fairness notion is feasible for a class of valuations, let's say for additive valuations, if for every allocation instance, there indeed is an allocation which is fair acceptable under this fairness notion. So the two notions that I described before are not feasible. So let's say envy-free is clearly not feasible. If you have just one item and two agents, whoever gets the item, the other agent will envy him. So there are relaxations of this notion. So instead of envy-free, people sometimes consider what's known as EF1, which allows some envy, but if I envy another person, there always must be an item in that other person's bundle such that if I remove that item, I no longer envy that agent. So this is an EF1 allocation. So it's envy-free up to one item. And EF1 allocations always exist. This is known. So they are feasible for any class of valuation functions. Also, the maximum share is known not to be feasible. For general classes of valuations, it's easy to show that it's not feasible. For additive valuations, this is a theorem. It's not easy to show it, but it's not a feasible fairness notion. But there are various relaxations of it that are feasible. One of them would be the MXS. So unlike the MMS, where an agent can choose the best possible partition and get the worst bundle in this partition, for the MXS, you look at the worst possible partition and the worst bundle in this partition, but the worst possible partition does not range over all partitions, but only on very good partitions, partitions in which all bundles have roughly the same value, in the sense that if you have two bundles that differ in value, any item that you remove from the higher value bundle, then the other bundle has at least as high value as what remains. So they are very balanced partition. You take the worst very balanced partition and the worst bundle in it, that's the MXS, and this is feasible. So these are examples of feasible fairness notions. So what does communication complexity have to do with feasibility? So if we have a feasible fairness notion, we know that an allocation always exists. So the problem is only find this allocation. And in this case, we expect the communication not to be too bad. And why is that? Because usually when you say that a fairness notion is feasible, you have an algorithm and like a proof that it is feasible. And this proof often is algorithmic. And often the algorithm runs in polynomial time. So often this would limit the communication also to being only polynomial communication. But if a fairness notion is not feasible, then the goal would be at first at least to determine if there is a feasible allocation or not. And this depends on like very minute details in the valuation functions. So maybe you'd need to explore the whole valuation function until you find out if there is a feasible or not allocation or not. So this might require exponential communication. So this is in terms of maybe what we would expect the results to look like. Okay, so here's a bird's eye view of the results. Okay, we'll start with general valuations. So if you look at feasible fairness notions, indeed we find that you can always find allocations using polynomial communication. And if you look at non-feasible fairness notions, as a rule of thumb, always you require exponential communication. And this was shown in a paper by Plaut and Raffgarten. If we look at item-based valuations, then for feasible fairness, the results appear to be more interesting. So in the sense, there's a mixture of results. Sometimes you need polynomial communication. Here, polynomial is not so good because you can communicate the full valuation function with polynomial communication. But sometimes you have just logarithmic communication would be enough, or even less. So the result starts being more interesting. And if we look at non-feasible fairness notions, so the communication in general would be polynomial. Like we don't appear to find this logarithmic communication appearing. So an interesting aspect of the result is what I refer to as full efficiency. So we say that communication is fully efficient if the total number of bits transferred by all agents combined is up to constant factors just enough to specify an allocation. So it means somehow that nothing in the communication was wasted. It's not that they did not have any idea of what to send and they start trying this or that. Like in a sense, they know exactly what they need to send in order to find an allocation. So the fact that the input is distributed over n different agents does not make any difference in up to constant factors. Even if just one agent had the whole input and would just compute an allocation and output it, it would be the same communication up to constant factors. And we have theorems of the sort that for some feasible fairness notions and some item-based evaluations, there are fully efficient randomized allocation algorithms. So in expectation, the amount of communication that they have is like the expected amount of communication if there was just, all the input was just with one agent who would need to transmit the allocation. Yes.
So efficiency, you just need to specify for each item which agent it goes to. So that would be m log n. Is that?
Okay. So a very good question. Okay. So one way to specify an allocation is to say for each agent for each item, which agent gets it. And so that's m log n. But you might not need to specify an arbitrary allocation. Maybe there's a small set of allocations such that just among them, one of them is necessarily acceptable, and then you can do it with fewer bits. So for full efficiency, you should meet this bound that uses the fewer number of bits. Okay, so it's not achieving m log n communications, it's even smaller. Okay, so now just some words about, is it reasonable to trust agents to communicate truthfully? So the way I look at it is, what would go wrong if agents don't report their valuations truthfully? So if we're looking at a fairness notion which is not feasible, and let's say the valuations were such that there was a feasible valuation, by cheating, they can prevent the algorithm from finding it. So the algorithm might not produce any allocation at all. So this would be a problem. Okay, so, and okay, we don't try to address it. But if we look at feasible fairness notions, we know that there always is an allocation. So if an agent cheats, he can like pretend to have a different allocation. The algorithm would still output an allocation, just with respect to the input that it received. And those agents that did not cheat still get their guaranteed. So the allocation would be fair towards the agents who did not cheat. So in a sense, if you care only about this fairness notion, we don't care if there are cheating agents. They can only help themselves. They don't help the other agents. Okay? So cheating is not a problem. But if you look at it more carefully, it is a small problem. Because if you look at randomized protocol and you look at the expected amount of communication in the protocol, by cheating, you can cause the communication to grow. So beyond its expectation. So you try to send those messages that would cause other agents to send longer messages and so on. So a way around it is if you have deterministic allocation algorithms. So in this case, there's an absolute upper bound on the amount of communication. And so usually, like what I would suggest is you start with a randomized allocation algorithm. If it starts going for too long, probably somebody is cheating, switch to a deterministic one, maybe a bit slower, but at least you have a bound on how much communication you'll have. Okay, so now I'll get to some more details on some results. So are there any questions before that? Okay. Okay, so let's start with general valuations. Any valuation, any monotone valuation, and two agents. So there is this notion of EFX allocations. So these are allocations in which if you envy another agent, then if you remove any item from that other agent's bundle, you don't envy him anymore. So this exists for two agents. This is known. So by the simple cut and choose protocol, one agent partitions the items into two bundles that seem roughly balanced to him, as balanced as possible to that agent. And then the other agent picks a bundle, and the first agent picks the other bundle. So this is a protocol. This is a feasible fairness notion here, and the protocol indeed is polynomial, just m bits, just to describe the partition. So that's a simple protocol. If we look at, in contrast at the MMS, maximum share, this is not feasible anymore. So here's an example. Suppose there's a row agent and a column agent. Okay, does it work? Okay, never mind. So the row agent, think of the four items arranged in this matrix, and the row agent wants a complete row. So from his point of view, the MMS is a complete row because there are two rows. Each agent can get a row. The column agent wants a complete column, and from his point of view, again, he deserves a complete column because each agent can get a column, but you cannot satisfy both of them simultaneously. So it's not feasible. So because of that, I said we would expect to maybe require exponential communication, and this is indeed true. So let me give a fast sketch of it. It's really not a difficult proof. So there is a known problem in communication complexity called set intersection, or sometimes its complement, set disjointness. So in this case, you have a set, and each agent has a subset of this set. The subsets might overlap or not. And you want to decide, they need to communicate and decide whether the subsets overlap. Like, is there an intersection? And it's known that the communication complexity of this, even for randomized protocols, is linear in the number of items. So how can we describe this MMS allocation as a problem of set intersection? So we create valuation functions that will achieve this. So for each valuation function, some sets of items of size m/2 will be acceptable and some would not be acceptable. And those which are acceptable would come in pairs. So if a set is acceptable, also its complement is acceptable. So for each agent, you have the list of pairs that are acceptable, and you have these two valuation functions, and they need to see if there's something in the intersection. Like if the intersection is not empty, then there's an allocation which is acceptable to both of them. And if there's nothing in the intersection, there's no such allocation. So there's an MMS allocation if and only if the sets intersect, but these sets are of exponential size now because there are exponentially many sets of size m/2. Okay, and there are many other negative results of this sort for non-feasible fairness notions and any number of agents and for general valuations. So yeah, okay, so there are some results also for approximate versions of this, as long as they are not feasible. Like once you reach fairness notions which are feasible, all the proofs of this sort break down. Yeah. Okay, so now let's look at general valuations and feasible fairness notions. So we said that if1, there's a polynomial time allocation algorithm. So indeed, you can do it with polynomial communication. MXS, we mentioned, there's also a polynomial time algorithm. So you can do it with polynomial communication. Somewhat more interesting would be contiguous EF1. So what's that? So you need, the items are arranged on a line from in an arbitrary order. So that's given to you this order from item 1 up to item m. And each agent needs to get a consecutive segment, like a set of items. Okay, so here the blue agent got the first 3 items, the green agent the next item, the red agent the next 2 items, and so on. And it's known that there are also EF1 allocations that satisfy this. So this is non-trivial. The proof is non-constructive. It uses Sperner's lemma. And no polynomial time algorithm is known for this. So the question is, can we find these allocations with polynomial communication, despite the fact that the algorithm is exponential? But the answer, in a sense, is, if you think of it a minute, obviously yes. And the reason is just because there are only m squared possible intervals. So each agent just needs to say, among these m squared possible intervals, what is the order among the intervals from his point of view? And you can communicate this with m squared log m bits. Okay, so that's another example of a feasible fairness notion in which polynomial communication suffices. So now let's get to what I think is the more interesting set of results. So these are item-based evaluations and for feasible fairness notions. And here, as I said, polynomial communication suffices because these are item-based evaluations, but sometimes we'll see that much less communication suffices. And sometimes we'll also see that randomized allocation algorithms offer full efficiency, like you waste only a constant factor in the communication compared to having just one agent know all valuations and output an allocation. Okay, so let's start just to illustrate why you can get logarithmic communication with a very simple example, unit demand. So the value of a set of items is the value of the maximum item in this set. And we'll consider the MMS, the maximum share. So what is the maximum share of an agent? So an agent can partition all items into n bundles, where each of the top n bundles items is in a different bundle. So the value of the MMS is like the value of the nth best item. So each agent should get at least one of his n top items. This is what we want to achieve in the allocation. So here's a simple protocol that does it. You take an arbitrary order among agents. Each agent in her turn selects a yet unchosen item. And then even the nth agent will get her MMS. So that's a simple protocol. And for the remaining items, you can give them all, let's say, to the first agent. It doesn't matter because they don't care about the remaining items. And the communication complexity is only log m bits per agent. So we have indeed shown logarithmic communication, and there's no need to send the full valuation function. Okay, so that's just illustrating the principle. So what are the results that we have? So let's go over them slowly. First of all, for unit demand, you don't need, if you allow, so this is now randomized protocols, if you allow randomization. So we look at the expected number of bits that they transmit, average per agent. So maybe a few agents will send a few more bits, some less bits, we take the average. So for unit demand, it turns out you don't need logarithmic communication. You can do it just with a constant number of bits. Doesn't matter how many items there are. A constant number of bits per agent suffices. For binary additive, so each item has values 0 or 1, and the valuation is additive. In this case, it's log m over n bits that you need to transmit. So if m is, let's say, linear in n, if the number of items is linear in the number of agents, it's still a constant number of bits per agent. But if you do a slight change, if the item of value 0, instead of having value 0, has very small value, let's say 1 over m, meaning that even all the small items combined are not worth even just one large item, then if you insist on MMS, this dramatically changes the communication complexity. You have an exponential jump from log m over n to m over n. If you look at NV-based fairness like EF1, if you look at the unit demand, you see that it's log n. So it's no longer constant. So NV-free based notions are somewhat more difficult than share-based notions here. And in all cases, you have like full efficiency. You see that except for the two-valued case, the 1 over m and 1, where you have full efficiency if the number of items is large. If it's smaller than m log n, I'm not sure. Okay. If we go to additive valuations, then the MMS is not feasible, and we want to look at feasible fairness notions. So if we look at the MXS that we mentioned before, it needs what I would say polynomial communication. So let's say even if n is equal to 2, just 2 agents, so each agent needs to send order m communication. There are other relaxations, feasible relaxation of the MMS. If we'll have time, we'll define them. I call it approximately proportional, approp. So it's two relaxing proportional allocations in which you get 1 over n of the total value in two different ways, one in the up to one item sense and another in an approximation sense, and doing it simultaneously. In these cases, we have very efficient protocols, just logarithmic. Okay, so for some relaxations of MMS, you need more communications, for some less communication. Okay, so these are the set of results. Okay, so let's look at some sketch of proofs for MMS allocations for classes of evaluation for which MMS is feasible. So I said that for unit demand, you can do it with order 1 communication. So let's see how it goes. So let's start with the case of just 2 agents. So where is the randomization here? The randomization is that the names of the items, we permute them at random. So the items have now random names. That's the only randomization. Apart from this, the protocol is deterministic. Okay. So what does agent 1 do? So agent 1 needs to get one of her 2 top items. So we looked at the binary encoding of these 2 top items and specifies which is the first bit in which they differ, and we'll start from the least significant bit. We'll start. So as an example, let's see bit points. Okay. So let's say the 2 best items are item 2 and 6, and these are their binary encoding. So the last bit they agree, so I transmit a 0. The bit before last they agree, I transmit a 0. And the bit before that they differ, so I transmit a 1. So that's what agent number 1 transmits. And then agent number 2, so this partitions all items into 2 sets. So those in which have 0 in this bit location and those that have 1 in this bit location. And agent 2 chooses which of these 2 sets she wants to receive. So she gets all the items in which the least significant bit is the value b that she chooses. Okay, so this is the protocol. So agent 2 gets her best item because she gets to choose which of the 2 parts she takes. And agent 1 gets at least one of her 2 best items, so at least her second best item. Agent 2 transmits only 1 bit, says which part she wants. And agent 1, in expectation, it's easy to see, transmits just 2 bits. So on average, they transmitted only 1.5 bits. Okay, so this is the protocol for 2 agents. So generalizing it to more agents, it's not trivial. This is used as a subroutine in the generalization, but the whole protocol is maybe too complicated to show in this short talk. So you can generalize it to more agents. Yes?
And what's the maximum for agents?
So I think it might not be bounded by a constant. It could be at most, probably. I have to think of it, but yes, at most log. Okay, it's a randomized protocol, so if the coin tosses go wrong, then it's hard to say, but it would not be worse than log m. I'm thinking maybe it's much smaller. Okay. So now let's look at binary 0-1 additive valuation. So each item has either value 0 or value 1, and it's additive. And let's look at the special case in which it makes things easier to present. The protocol is more general. Let's look at the special case where m is order n. So the number of items is like linear in the number of agents. And then in this case, we'll show that the communication complexity is still order 1 bits. Okay? So each agent has a desired goal of how many items of value 1 it needs to achieve. So if, let's say, there are k times n items of value 1, then it should receive k such items in MM, okay? So each one has his own value of ki, how many items of value 1 it needs to receive, and it transmits it. So this takes log m over n bits to transmit it because the value is not larger than m over n. And so when m is linear in n, that's a constant number of bits. Okay, so so after we have these numbers, we sort the agents in order, or in increasing order, from the smallest to one with the smallest demand to the largest demand in terms of items of value 1 to herself. And so this part is deterministic. The only random part is arranging the items at a random order. So that's the random part of the protocol. Then in each agent, in her turn, cuts an MMX prefix of the reminder. So the first agent says, I need to receive K1 items of value 1. He starts scanning the items. Once he reaches K1 items of value 1, he cuts and takes this part. The second agent says, I need to take K2 items of value 1. So again, he scans the remaining items. When he reaches K2 items of value 1 for himself, he cuts and takes it, and so on. That's the whole algorithm, except for the last step, okay, almost. So this part, the total communication is order m because we just have cuts in a sequence of length m. So amortized per agent is order 1. Some agents would cut later, some earlier. But the problem is, are there enough items for each agent to be able to get a bundle? Maybe at some point we run out of items and we still have agents left. So the leftover agents, we need to do something with them. So we have a procedure of them, which I will not describe here, stealing items for agents that already received items. And the basic idea is because, let's say I'm an agent towards the end, I needed to take, let's say, 5 items. And an agent in the beginning needed to take only 2 items, but he might have taken more than 2, let's say, items that I wanted. Then I will steal from him an item. I need to point at which item I want, or some negotiation if he's willing to give it up. But it takes log m communication per item that I need to steal. So if you see, so the problem is in this protocol, how much communication do we need for the leftover agents? How many leftover agents are there? They're the expensive part of the protocol. They need to steal the items. So if there are fewer than n over log n agents left over, we're fine. We can afford to let them steal items. Log n and log m are the same because m and n are the same up to constant factors. Okay, so that's what we need to show. So let's see why we expect this to happen. If we have an arbitrary order over the items, then if we have identical evaluations, it's easy to see that no item would be, every agent would get items and will not have the second phase of the algorithm at all. But if they have different valuations, then it might be that the first agent, all the items that it values were towards the end, and when he scanned the list of items, he cut it towards the end, and then the other agents don't have enough. Maybe their items were towards at the beginning, they're good items, and they don't get anything, and a lot of agents remain. So for this reason, we needed the random order. So this was the reason for the random order. And then if you look at it, for the first agent, you expect it to cut after roughly m over n items. So if you could say that this persists for the other agents, that would be easy, but there are dependencies between agents, okay? So this complicates the proofs because their valuation functions might be somehow correlated. And because of this reason, the proof becomes more complicated, and eventually we use some martingale concentration inequalities to show that not too many agents are left over at the end. Okay, I'll not show the proof. Okay, Okay, so let me give an example of how we prove lower bounds on the communication complexity. So this is, in a sense, as I said, our protocols are fully efficient. So really, in a sense, we're also saying what's the lower bound on the communication complexity, even if all evaluations are known to a single agent who computes an allocation and needs to transmit it. So it's even stronger lower bound. So we use a version of Yau's minimax principle. So we will show a distribution over valuations such that for every allocation, the probability that it is acceptable is very small, is 2 to the minus, let's say, t. So this implies that the randomized communication complexity is at least t. You need at least t bits, or at least t over n per agent. So this implication needs a proof, but it's not a difficult proof, okay? So if you can show that a distribution over allocations, over valuations, such that every allocation has very small probability of being acceptable, it means that you need a lot of communication to describe the allocation that you chose. Okay, so let's see an example. What changes if instead of 0, 1 valuations, we have 1 over m and 1 valuations? The difference is that in the 0, 1 valuation, we didn't care what happened with the 0 items. We could give it to any agent that we wanted. But with 1, if these items are worth even a little bit, for MMS, we do care who gets them, and this makes the whole difference. So in the example, all agents will have the same valuation function in the distribution that we will create. And in this distribution, there will be n times k minus 1, not n times k, just 1 less, items of value 1. So each agent should get k items of value 1, but one agent would get k minus 1 items of value 1. And all the remaining items are small. They have value 1 over m. So their combined value is smaller than 1. But the agent who got k minus 1 items of value 1, he has to get all these items. Otherwise, it's not an MMS allocation. Okay? Whereas when items were of 0 value, we didn't care how we distributed those small valued items. So in every MMS allocation, n minus 1 agents each get k large items, and one agent gets k minus 1 large items. And then that agent needs also to get all the small items. So if it's pick just a random valuation function with this property that nk minus 1 items are large, then if we look now at every potential MMS allocation, what is a potential MMS allocation? So it's n minus 1 bundles of size k, and the other bundle with all the other items. So if we look at such an allocation, and now we choose at random the valuation, the probability that the valuation, that this would be acceptable for this valuation, this would happen only if all the small, none of the small items is in any of the bundles of size k, but this has exponentially small probability of happening. So this implies that you need communication, which is the log of exponential in n, so you'd need order m total communication, or order m over n communication per agent. Okay, so I think in terms of time, maybe I'll leave some time for... So there are results for general additive valuations. We said MMS is not feasible, and MXS is feasible, and we have a different notion of a feasible share, which we call approximately proportional, which I will skip over because we are running out of time. So the main point is that for this approximately proportional, you have very efficient protocols, order log m communications, but for MXS, think of n as being small, compared to m, we don't have efficient protocols. And the protocols, the efficient ones are variations on known protocols for cutting a divisible cake, protocols from 84 by Evan and Paz, and some variations on them. So I will not describe them. So let's remind ourselves of our results in what I find the more interesting case of item-based valuations and feasible fairness notions. So for MMS, when it was feasible, we essentially almost always got full efficiency, except, let's say, in this two-valued 1/M1 case where if the number of items is not sufficiently large, we don't know. So this is maybe open. Can we get also in that case full efficiency? And for general additive evaluation, and when we don't look at MMS but other fairness notions, for MXS, we have a lower bound, and for this approp notion, we also seem to get full efficiency, except when there's a small number of items. So let's get to the open questions. So to show that the full efficiency holds also in the cases that we could not figure out, so here's a concrete question if you want to think about it. So think of arbitrary additive valuations, a fixed order of the agents, so you don't get to choose the order from agent 1 to agent n, but there's a random order over the items. And the question is there a, we show this protocol in which each agent cuts at his turn items from the prefix when he achieves an acceptable bundle. So here being acceptable means prop 1, meaning that if I add one more item that I don't have in my bundle, then the total value of the bundle would be at least the complete total value of everything divided by n. And the question is it likely if I choose a random order that this cutting procedure would satisfy all the agents? No agent would be left over. And if this is true, then it will achieve full efficiency for prop 1 and probably also for this approp that I mentioned. So we have full efficiency in more situations. Perhaps the more interesting question is the other direction. Show that there are feasible fairness notions for which you don't have full efficiency, that the fact that the input is distributed over items causes a problem for you. In fact, I don't know of an example for this. So as a concrete thing to try is for MXS, does it require, let's say, with the communication complexity never needs to be more than, okay, the description complexity of an allocation is never more than m log n. Is the communication complexity larger than m log n? For additive valuations or even for general valuations, can you show that you need more than m log n communication? So that's another open question. Okay, I'll end here. So.
So we have some time for questions.
Like, how much do you think the landscape changes when we look at chores instead of goods?
Okay, so I did not look at chores, but so let's say it's open. So people are welcome to look at it. I don't know. Yeah. I would assume that the principles are similar in the sense that if you look at feasible fairness notions, they require less communication, item-based, you'd see interesting things going on, things like that. But what the exact results would be, I don't know. Yeah.
So,
Sorry, again?
So in the algorithm for value item, suppose we take the items that are valued in the phone prefix.
Yes.
Does it help or does it blow up the communication complexity?
So the problem is that suppose that so I showed the case where like m was order n, think of m being much larger. So in that case, if okay, if you want to specify which items are valuable for you, so in a sense, this happens to some extent with some of the agents, those which are left over. But if you try to do it for all the agents, like specifying an item is something like log m, it becomes more problematic. Here, the point is that I'm using the fact, another way to explain it, it's this distinction between the case of 0, 1 and 1 over m and 1. In 1 over m and 1, in a sense, you needed to do what you said here, to say which are valuable to you, and for those which are not valuable, you needed somehow to give them to the other agents, to give them up. In the 0, 1, you don't need to give them up, and for this reason, you get more efficient protocols. That within the bundle that you get, you don't specify which items were important for you and which were not. This is like what makes the protocol more efficient.
Okay, thanks.
Yeah.
So, going back to the very initial setup, the communication from the agents is revealing information about their valuation functions to
Yes.
the algorithm, and then this information is immediately available to all agents.
Yes.
So when the agents trust the centralized allocation authority, but not other agents, if we want to limit the information revealed to other agents, what kind of communication model would work in such a setting?
So basically, okay, so it's hard to tell here what an agent learns about valuations of other agents, in the sense that even if I just communicate with the center, the queries that I get depend on what the other agents send. So I will learn something about the others.
Right.
I will not learn more than the number of bits that they send, that's for sure. And so for this reason, like protocols with low communication are good. They don't reveal much information, but I don't know to say anything.
Is it plausible that actually more can be hidden?
It is plausible, yeah. You learn something if you see the full allocation at the end. You don't need to see the full allocation. Maybe you just see what's allocated to you. But also just by seeing the full allocation, you also learn something about the valuation of the others. But if you just get your own allocation, so for things like share-based fairness, that's okay. You just need to see your own allocation, what you got. But if you look at envy-based notions, you want to know what the others got, and then you certainly learn something about their valuations. So I think it might depend on the fairness notion, how much you learn about others.
Okay, so if there's no more questions, let me ask the brownie question, which is that all of the fairness notions we saw are ex-ante fairness. What are two other fairness notions which Uri mentioned at the beginning of the talk? So besides ex-ante fairness, what were two other fairness notions that?
Sorry to say.
I'm sorry, exposed. Exposed, I'm sorry.
So part of the answer is in the question.
I apologize. Yes. So one of them is ex ante. What is another one? Yeah, procedural fairness. Thanks. Okay. So I'm going to ask Aditya. Is Aditya here? I'm going to ask Aditya, who's a volunteer, to present this set of puzzles to Uri as thanks for his talk.
Thank you. Hi. Thank you.
Great. Thank you so much, everyone.